Welcome back, ladies and gents. In this teaching video, I'll be looking at 6.4 projectile motion formulae. 6.4 represents chapter 6, section 4 of the Pearson A Maths Applied Maths Year 2 textbook. I'm going to start this teaching video by going through exam style question 1. A particle is projected from a point O with speed u meters per second at an angle of elevation alpha above the horizontal and moves freely under gravity. When the particle has moved a horizontal distance x, its height above O is y. Show that y is given by x tan alpha minus gx squared all over 2u squared cos squared alpha. Okay, so I'm going to first of all start off by drawing a diagram to model this situation. So we have a horizontal ground. Here is the point O. The particle is projected at u meters per second, forming an angle alpha above the horizontal. Here is the pathway of the particle. The particle strikes the ground at this point over here. We have acceleration due to gravity acting vertically downwards, g meters per second. Now for this speed over here, we have component speeds. We can form a right angle triangle. Put in our arrows. This over here is the adjacent, so it will be u cos alpha. This here is the opposite, so it will be u sine alpha. Okay, consider this point over here to be point A. Now the horizontal distance, we can call it x, and the vertical distance, we can call it y. Right, so now I'm going to take motion O to A and I'm going to try and derive this particular beautiful equation. So we have motion O to A. Ladies and gents, we can split the motion into two parts, horizontal and vertical. So horizontal, taking right to be the positive direction. Then we have vertical, taking upwards to be the positive direction, because the particle is moving upwards from its point of projection. Right, now for the horizontal, we have S equal Vt. The horizontal displacement from O to A is x. The horizontal initial velocity is u cos alpha. And the time is just t. Right, so we can make t the subject. This gives us t equal x over u cos alpha. I can call this equation 1. Now let's have a look at the vertical. For the vertical, we have SUVAT. So if we're looking at motion O to A, the vertical displacement is y, as you can see from the diagram. The vertical initial velocity is u sine alpha. The vertical final velocity at the point A, we don't know. Remember, point A is not the maximum height, so we don't know that velocity. We can just put an x here. The acceleration is just going to be minus g, because we're taking upwards to be the positive direction, and the time taken to move from O to A, we don't know. We can just call it t. Okay, so now we can use the SUVAT formula to plug in these quantities. So the SUVAT formula that I'm going to be using is S equal ut plus a half at squared. So I've got S equal ut plus a half at squared. Now I can carry out my substitution. I've got y equal u sine alpha multiplied by t plus a half multiplied by minus g multiplied by t squared. So I can clean this up and I can write y equal u sine alpha t minus a half gt squared. We can call this equation 2. Okay, right, so if I go back to what I need to derive, we don't have t's involved. So over here, we need to eliminate the t's. So we're going to substitute equation 1 into equation 2. Right, so if we do that, we get y equal u sine alpha multiplied by the t, which is x over u cos alpha, minus a half g t squared remember t is x over u cos alpha. We are going to square this. Okay, so now we're going to simplify. Notice that the u's cancel, and we have sine alpha over cos alpha, which is just tan alpha, so we get x tan alpha. Right, now over here we're going to get minus a half g multiplied by, if we square this fraction, we get x squared over u squared cos squared alpha. Right, okay, so if I further simplify, I get y equal x tan alpha minus gx squared all over 2u squared cos squared alpha as required. And so that there, ladies and gents, completes the question. And that's why this section is called projectile motion formulae. In the exam, you could actually be assessed on deriving a formula. And that's what I've done over here. So now things are more abstract. But to be fair, the method is still consistent. Split into horizontal, split into vertical, set up two equations, carry out substitution, and you'll get the desired form. Here is exam style question 2. So this over here is a diagram used to model the motion of a ball. So the ball starts at the point A. It is projected at a speed of u meters per second, forming an angle alpha above the horizontal. The height from here to the point A is 2 meters. The ball travels in such a way that it reaches its maximum height of 3 meters at the point B. It then continues to travel to the point T, and the height above the horizontal ground at the point T is 0.75 meter. The horizontal distance from the point of projection to the point T is 20 meters. Now what we have over here is acceleration due to gravity acting vertically downwards. G meters per second per second. For this speed we have component speeds. So I can form a right angle triangle, put in the arrows. This part over here is the adjacent, so u cos alpha. This part over here is the opposite, u sine alpha. Okay, ladies and gents, using the model, show that part A, u squared is equal to 2g over sine squared alpha. Let's do this. Right, so part A, I'm going to take the motion A to B. So we've got horizontal, taking right to be the positive direction. We've got vertical, taking upwards to be the positive direction, because from this point of projection, the particle, or you could say the ball, is projected upwards. Okay, so first of all, with the horizontal, we have S equal Vt. The horizontal displacement from A to B, we don't know what that is, we can just call it x. The horizontal initial velocity from A to B is u cos alpha. And the time is t. Okay, so that there doesn't really help us derive this particular formula. So let's move on to the vertical. For the vertical, we have SUVAT. So we're looking at the motion from A to B. Vertical displacement would just be 1. The gap between 3 and 2 is 1. So that part there is just 1. Okay. The vertical initial velocity is u sine alpha. The final velocity at the point B, which is the maximum point, will be 0. The acceleration will be minus g, and the time taken will be t. Okay, so what we want is this particular result over here. How do we get this? Well, if we go back here, there's no t's involved. So I want to use a SUVAT formula that is independent of t. And that SUVAT formula that I can use in this particular scenario is v squared equal u squared plus 2as. So we have 0 squared equal u sine alpha squared plus 2 multiplied by minus g multiplied by 1. Okay, so we can clean this up. We've got 0 equal u squared sine squared alpha minus 2g. Okay, so now I can just rearrange. So if I rearrange, I get u squared sine squared alpha is equal to g. Hence, u squared is equal to g over sine squared alpha as required. That's what we needed. Let's have a look at part B. Find the size of angle alpha. To find the size of angle alpha, I'm going to take into consideration the motion from A to T. Okay, so let's do part B. Motion A to T. So we can split it into horizontal, taking right to be the positive direction, and vertical, taking upwards to be the positive direction. So horizontally we have S equal Vt. Now from A to T, the horizontal displacement is 20. The horizontal initial velocity from A to T is u cos alpha. The time taken for the ball to reach T we don't know, so we can just label it as lowercase t. So now I can make T the subject. This gives me T equal 20 over u cos alpha. Equation 1. Now for the vertical we have SUVAT. The vertical displacement from A to T. To get that, we need to do 2 take away 0.75. That's 1.25. And because upwards is the positive direction and the ball travels downwards by 1.25, the displacement will be minus 1.25. The vertical initial velocity from A to T is u sine alpha. The final velocity at the point T, we don't know. We can just put an X there. The acceleration would just be minus g. And the time taken, we don't know. From A to T, we can just call it lowercase t. Okay, so now I'm going to use a SUVAT formula to put these quantities in. And the SUVAT formula that I'm going to be using is S equal ut plus a half at squared. Okay, so I can write this down. Plug in all the values. So we have minus 1.25 equal u sine alpha t plus a half multiplied by minus g t squared. If I clean this up, I've got minus 1.25 is equal u sine alpha t minus a half g t squared. We can call this equation 2. Okay guys, right, so I've got equation 1 and I've got equation 2. If I substitute equation 1 into equation 2, that will eliminate the t's. But the problem is I still have a u involved and I still have an alpha involved. In order to solve for alpha, I need a complete equation involving alpha only. So I need to also eliminate the u as well as the t. So how do we eliminate that u? Well, we're going to have to go back to our result that we derived in part A. So I'm going to be using that result in order to eliminate the u completely in this equation, arriving at an equation involving alpha only. Right, so first of all, I'm going to substitute equation 1 into equation 2. Okay, so substitute equation 1 into 2. This gives me minus 1.25 equal u sine alpha multiplied by t. So 20 over u cos alpha minus a half g multiplied by t squared. So 20 over u cos alpha squared. Right, so over here I notice that there is a beautiful cancellation that takes place. The u's cancel over here. The sine alpha over cos alpha becomes tan alpha. So we have minus 1.25 is equal 20 tan alpha. Okay, minus a half g. Right, over here 20 squared is just 400 all over u squared cos squared alpha. Right, so we're going to further simplify this. We have minus 1.25 equal 20 tan alpha minus 400 divided by 2 is just 200. So we have 200 g over u squared cos squared alpha. Okay, so now we've got an equation involving alpha, but we also have the u squared. We're going to have to eliminate the u squared using our result in part A. Okay, so if we use that result, I'm going to take the calculation over here. We have minus 1.25 equal 20 tan alpha minus 200g over cos squared alpha multiplied by 1 over u squared. So I can split this fraction into a product of two fractions. Okay, so what will the 1 over u squared be? It will just be the reciprocal of this. So it will be sine squared alpha over 2g. So that there is just sine squared alpha over 2g. Okay, so we have minus 1.25 equal 20 tan alpha. The g's will cancel over here. 200 divided by 2 is just 100. So minus 100. Sine squared alpha over cos squared alpha is just tan squared alpha. Absolutely brilliant. Oh my god, look at this. So we've got an equation involving alpha only now. Hence we can now solve for alpha. I'm going to take everything to one side. Okay, so if I do that, I get 100 tan squared alpha minus 20 tan alpha minus 1.25 is equal to 0. So we've got a quadratic trigonometric equation we can solve to work out the two values of tan alpha. So if we solve this, we get tan alpha is equal 1 over 4 or tan alpha is equal to minus 1 over 20. Okay, so this equation here gives us alpha equal 14.1 degrees, and this particular equation over here gives us alpha equal minus 2.9 degrees. Okay, so the suitable value for alpha that we take is this one over here. Okay, alpha is equal to 14.1 degrees because it's positive, as you can see from the diagram. Okay, ladies and gents, that there completes part B. Okay, so we've done part B. We've worked out the two possible values of alpha, 14.1 degrees minus 2.9 degrees, both rounded off to three significant figures. We've taken 14.1 degrees to be the correct answer because alpha over here represents an angle of elevation. So it is a positive angle. Let's proceed further. Let's have a look at part C. State one limitation of the model that could affect your answer in part B. Okay, so there's more than one answer here. We've neglected air resistance. We've neglected the rotational spin of the ball. We've also neglected the effects of wind. So any of these over here are sensible answers. Right, in part D, we want to work out the time taken for the ball to travel from A to T. Okay, so to do this, I'm going to quickly rub out part A. I need space for this, ladies and gents. Okay, so I can get rid of part A. Okay, so for part B, we want to work out the time taken for the ball to travel from A to T. We know that the time is given by 20 over u cos alpha. So, T is equal 20 over u cos alpha. We can split this as T equal 20 over cos alpha multiplied by 1 over u. We know that u squared is equal to this fraction. So since u squared is equal to 2g over sine squared alpha, u would equal square root of 2g over sine squared alpha. We've taken the positive square root because u is projected upwards, and we've taken upwards to be the positive direction. Okay, so now, if u is equal to this, we know that 1 over u will have to be the reciprocal of this. So it would just be square root of sine squared alpha over 2g. Okay, so now I can substitute to work out t. So t is equal 20 over cos alpha multiplied by square root of sine squared alpha over 2g. So if I use laws of surds, I can take the square root of the numerator, divide by the square root of the denominator. So the square root of the numerator will just be square root of sine squared alpha, which is just sine alpha. Okay, divide by square root of the denominator is square root 2g. So sine alpha divided by cos alpha is just tan alpha. So I've got 20 over square root 2g multiplied by tan alpha. But I know what tan alpha is equal to. Since we've taken alpha to be 14.1 degrees to three significant figures, we have to take tan alpha to be a quarter. So I've got 20 over square root 2g multiplied by a quarter. And so in exact form, it will just be time at the point t will be 20 divided by 4, which is just 5, over square root 2g seconds. Okay, so that there is the time at the point t. And that there, ladies and gents, is the end of exam style question 2. If you found this video useful, please don't forget to leave a comment, tap the like button, tap the subscribe button, turn on the notification bell, and stay tuned. I'll be producing more videos.